This is a new character controller I've been working on. The one I've been using in the last devlogs has been getting a bit messy, so with a better understanding of what I want out of my character controller, I built this new one as a proof of concept. It doesn't have all the movement mechanics I've previously shown yet, but it fixes a lot of subtle issues that were hard to address without a rewrite. I've also been wanting to make a more technical video, so I figured this could be a fun opportunity to make a very technical video where I walk through the entire process of remaking the character and camera controller for my movement shooter. This is an admittedly long video, but you can think of it kind of like a Twitch VOD with all the filler removed. I'm actually a bit worried the pace is too fast, but there really is a lot to cover. If you stick around, you can see what all is going on under the hood and maybe learn something, or you can just tell me how awful the code is. There will definitely be some 3D math involved, but as long as you're familiar with these guys, you should be fine. With that out of the way, we've got a lot to cover, so let's get to it. I'm going to start by closing the project and opening a mostly blank one. I just have a scene with a flat terrain, and I've imported the Kinematic Character Controller asset. This is the asset that I use as a foundation for my custom character physics. It's not a drag and drop character controller like some others you might see on the store. Rather, it's more of a framework for you to build your own physics on top of. In addition to the character controller, I've gone ahead and installed the input system package. The first thing I'd like to do is create the player's input actions. This input actions asset will map specific inputs to the actions the player can make. For this character, I'm starting with the basics. The mouse rotates the character, WASD moves it, spacebar jumps, and control crouches. I've got an empty player game object in the scene, but before we add anything to it, I want to quickly break down the structure of the player we're going to make. At the top level, we'll have a player class. This will be the glue that binds all the player's logic together. Its main responsibility is telling the player character and player camera classes what to do. The player character will handle the player's movement, and the player camera is just the camera. The only scripts that will have any Unity event functions, like start or update, will be the player. The rest of the scripts will have their own initialization and update functions, which the player will call manually. I personally prefer having explicit control over when everything runs. This requires a small amount of extra setup, but in my experience, it keeps things easier in the long run. Okay, let's stub in the player character and player camera game objects. And then under the character, I'm going to create a root game object where I'll throw any player graphics. For now, I'll just use a capsule. The character controller will have its own capsule collider, so this object doesn't need any collision. Under the camera game object, I'm going to create a main camera which will hold the actual camera component. Later on, I'll be adding more parent transforms to the main camera, which will each add a layer of procedural animation to the camera's movement. Next, let's create a script for the player, player character, and player camera, and assign them to their respective game objects. The first thing I want to do is open the player character script and implement the iCharacter controller interface. This interface comes from the Kinematic Character Controller asset. It provides all the methods needed to define a character's physics. With that implemented, I'll now add a kinematic character motor component for our character controller to hook into. This component has a bunch of settings for how the character will resolve collisions and solve any movement we tell it to make. To hook in our character controller to the motor, we'll need to assign it from code. I'll assign the character to the motor in a new initialization function in the player character, and then I'll switch over to the player class and add a reference to the player character so its initialization function can be called on start. After assigning the player character to the player in the inspector, I'll create a new camera target game object. This will represent where the character wants the camera to be positioned. I'll add a private field to the player character that references its camera target, and then add a function that exposes it to the player. After assigning the player character's camera target and motor fields in the inspector, we can now hook up the camera to the player. Just like for the player character, I'm adding a new field for the player camera and stubbing in its initialization function that gets past the camera target. To start, the player camera will snap its position and rotation to the target transform's position and rotation. After hooking up the player camera to the player in the inspector, the camera now snaps to the camera's target when the player calls its initialization function on start. Now before doing further work on the camera, we need to set up the player's input actions on the player. This input actions class is generated by the player input actions asset we created earlier. Hopping back over to the player camera, I'm going to create two new functions. one for updating the camera's position, and another for its rotation. The position update is pretty simple. It will just get past a camera target and then snap its position to it. The rotation of the camera will be based on its mouse look input. I'm going to create a new struct to hold that input, which will be passed to the update rotation function from the player. It'll only store one field for now, but we can add more to it in the future if needed. Now that we have our look input, we can rotate the camera. But rather than rotating the transform directly, I'm going to create my own field to store the camera's Euler angles. This is because the transform's Euler angles property is just a wrapper around its quaternion. While the Euler angles will always have an equivalent rotation to the quaternion, the angles can change unexpectedly and wrap around 360 degrees. This isn't necessarily a problem, but I like to store the angles myself so they change exactly how I expect them to. I'm now going to offset our Euler angles field by the look input, and then assign it directly to the transform's Euler angles property. Over in the player, we can now create the camera input and pass it to the player camera. Then at the end of the frame, after the player's character has updated, the camera's position can be updated to match. With the camera being updated, I can now look around the scene. The sensitivity is way too high, so I'm going to add a quick variable to the player camera to control it. That feels better, but I'd also like to lock the cursor when the game view is focused in the editor. We can do this by setting the cursor's lock state to locked. This will hide the cursor and lock it to the center of the game view, though its behavior is a little bit different in builds where pressing escape doesn't unlock the cursor. Now the camera rotation feels correct, but the character's body is not rotating to match. Similarly to the camera, let's create an update function and input struct for the player character, which will track all the input it needs to handle, like jumping and crouching. For now, it will just store the camera's rotation, which will be used to orient the character and its movement. Switching back over to the player character, we can handle the character's input. But first, let's talk about game loops. This update input function is called every frame by the main game loop, but the update velocity and update rotation functions are called every physics tick by the character motor. The update input function could get called more than once between physics ticks, or not at all. So the purpose of this function is really just to queue requests for the character controller to execute on its next physics update. We could store a copy of the character input in a member variable for the update rotation and velocity functions to check, but making a distinction between raw input and actionable requests will make things easier in the near future. So I'll create a variable for the requested rotation and assign it from the update input function. In the update rotation function, we're passed a reference to the character's rotation quaternion, which we can set to whatever we want. Since we want the character to look in the same direction as the camera, let's just assign its current rotation to the requested rotation and see what it looks like. As you can see, the character is pitching up and down with the camera. We just want it to rotate around its up axis. So to prevent the player from looking up and down, we need to calculate its planar rotation. We can do this by getting the direction the camera is facing and projecting it onto a flat plane. This gives us the flattened look direction of the camera, which the character can be rotated to face along. The flat plane will be defined using the character's up axis as its normal, not a global up vector. In the future, I may want to completely change the direction of gravity or the player's orientation, so I'm trying to keep that in mind when I'm doing all the math. Now, instead of assigning the current rotation directly to the requested rotation, let's use our new forward axis to create a rotation that looks along the movement plane. Now the character looks in the same direction as the camera without pitching up and down. Next, let's add some player movement. I'll start by adding a move vector to the character's input struct, and then I'll define a new variable for the character's walk speed. As with the requested rotation, we'll also have a requested movement. It'll be the update input function's job to take the raw input vector from the character input and translate it into a requested movement vector for the character controller to use. So we'll take the 2D input vector and turn it into a 3D vector on the XZ plane. Now when using WSD, the input vector will actually be longer when moving diagonally. So to prevent the player from moving faster diagonally, I'm going to clamp the requested movement's magnitude to 1. Finally, I need to orient the requested movement to face in the same direction as the player. We can do this by simply multiplying the requested movement by the camera's rotation. Now we can switch over to the update velocity function, and in the same way we're writing to the current rotation in the update rotation function, we can write to the current velocity to set the character's movement direction and speed. Let's just start by setting the current velocity to our requested movement vector and see what it looks like. Oh, and also we can't forget to hop over to the player and update the character input struct with the movement input. It appears to work at first, but if I look up and walk forward, you'll notice something weird. The higher I look, the slower the character moves, not to mention it's hovering over the ground. There are two reasons this is happening. The first is that our requested movement vector is rotated relative to the camera, so forward is in whatever direction the camera is facing. That means I'd expect the player to walk up into the air when looking up and pressing forward. The reason it doesn't is actually due to the second reason, the kinematic character motor. Whenever the character is on the ground, the motor will try and stick to the ground unless it is explicitly told to unstick or the character is moving past a certain speed threshold. Because we're essentially walking slowly in the air, the character isn't moving fast enough to unstick automatically, and the character controller tries to stay stuck to the ground. Sticking to the ground is normally a good thing because it prevents the character from getting air when walking over small slopes. We're just getting weird behavior because we're asking the character to walk directly up into the air rather than along the ground surface. So instead of assigning the current velocity directly to the requested movement, I want to get the requested movement projected onto the ground. So I'll create a new variable for the grounded movement. And then we can use a function from the kinematic character motor to snap it to the ground surface. The direction will be our requested movement vector, and the normal will be the ground normal detected by the character motor. Now we can use the grounded movement instead of the requested movement, but we need to remember that getDirectionTangent to surface returns a unit vector, so if we want to preserve the magnitude of our movement, we need to multiply it first. Now when I walk around, even if I look straight up into the air, the player moves at the same speed. And the character also doesn't hover over the ground. Now really quickly, I just want to get rid of that look rotation viewing vector is 0 log in the console. So I'm just going to add a quick check where we only calculate the look rotation if the forward vector is non-zero. Now this would only really be an issue if you look directly up or directly down, so the only reason this is even possible is because I don't have any limits on how high up and down the character can look. I kind of like being able to do flips in the air, so I'm just going to leave it alone for now. Next up, let's add jumping and gravity. As always, we'll start with adding some variables. I'll add a field to the character input for jumping, and 2 new fields to the player character for jump speed and gravity. Finally, I'll add a bool for whether or not the character wants to request a jump, and we'll set it to true when the jump input is pressed. I'm also setting it to true if it's already true, since the update input function can be called multiple times before the next physics tick, and I want it to stay requested until the character controller has time to check it. So we want to request the jump if it's already being requested, or just now being requested, and it'll be set to false once it's been checked during a physics update. Let's pop over to the player real quick so we can update the character input. Then we can hop back and add jumping and gravity to the update velocity function. In the update velocity function, the character should only move when it's on the ground, and should only have gravity when it's in the air. So let's wrap the movement in a check to make sure the character is actually on the ground. If not on the ground, the player is in the air, and we can apply gravity. This will just be a force on the character's up axis multiplied by the gravity variable we created earlier. Now we can check if the character is requesting a jump. If the jump is requested, we'll unset the request, unstick the character from the ground, and then add a jump force. So let's test it out. Jumping seems to be working fine. The player can jump as many times as they want in the air, which I guess I'm okay with for now, but I'm not sure if adding a force is exactly how I want the jump to work, because if the character is falling really fast and tries to double jump, the jump just adds a force, which slows the fall but doesn't necessarily feel like a jump. So what I'd actually like the character to do is set its minimum velocity along a jump axis, not add a force directly. I could do this by setting the y velocity to the max of its current velocity or the jump speed, but this would prevent jumping from working for arbitrary orientations, like on a spherical planet. This makes the math a little bit more complicated, but if we do it right, it will make the character controller more robust in the future. To set a minimum vertical speed, I first want to know the current vertical speed. The velocity's length along an axis tells us its speed along that axis, so we can just get the dot product of the current velocity against the character's up axis to get our vertical speed. Then we calculate a target vertical speed by taking the max of the current vertical speed and our jump speed. The final jump force will just be a difference between the current and target vertical speed along the character's up axis. Alright, let's see how that works. Now double jumping definitely feels better. When I press the jump while falling, the player actually jumps upwards rather than just slowing down. With basic movement in place, I'm going to build out the sandbox environment a little bit more so there's stuff to test the movement on. I'll start by painting some quick hills, and then a little trick I like to do to make the terrain feel more organic and a little stylized is to swirl the height map around with the twist tool. This creates a fun swirly terrain that looks more believable than a bunch of random mounds, and it plays well with the sliding mechanic that we'll implement later. And then anywhere that looks a little bit too steep, I'll clean up with the thermal erosion tool to smooth it out a bit. I also want to add some ramps and floating cubes to the level so that as we continue adding mechanics and refining the character controller, we have some more stuff to test precision movement on. So here's the simple sandbox level I've created, which gives us something to actually test character movement on and see how it feels. Right now I'd say it feels pretty bad. The character controller has zero control when jumping in the air, and the ground movement is not smooth at all. It's pretty easy to walk off of platforms, and precision jumping feels almost impossible. Before we start polishing up how it feels, I want to first add player crouching. Once that's set up, we'll have most of the player mechanics implemented and can do an initial polish pass to make it feel way better. To kick off crouching, I'm going to start by creating a crouch input enum. Crouch input is an enum rather than a bool because some players will want to hold the crouch button while others will want to toggle it. For now, I'm just going to implement toggle crouching, but it won't be hard to add a hold to crouch setting in the future by adding those crouch inputs to this enum. I also want to track the stance of the character so we know if it's currently standing or crouching, so that'll be a new enum as well. The character will move slower when crouching and have a shorter height, so let's define the crouch speed variable as well as the crouching and standing height variables for the character. To keep track of the character's stance, I'll add one last variable using the stance enum we just wrote. The stance will be initialized to standing, so the player is not crouching when the game starts. And then I'll create a new variable that stores whether or not the crouch is currently being requested. It will then be the update input function's job to read the crouch input from the player and change the requested crouch bool accordingly. Oh, and I actually forgot to add the crouch input enum to the character input struct. So with that added, I'm using a switch expression to flip the crouch request when the crouch input wants crouching toggled, and to leave it the same if not. This is where you could handle additional crouch input enums for holding to crouch or releasing to uncrouch. Now that the crouch request is being set correctly, let's actually make the character controller crouch when it's requested. The iCharacter controller interface we're implementing here has methods which are called by the kinematic character motor before and after the character controller updates. I'd like the character to handle crouching before its movement logic runs in the update velocity method, so we'll handle crouching here. But I also want to handle uncrouching after the character updates, because it will require some extra logic to prevent the character from uncrouching into ceilings. So if the player has requested a crouch, and it's standing, we know the character should begin crouching this frame, and can resize the character capsule to its crouch height. For uncrouching, I'll do the opposite. If the player is not requesting a crouch, and is not standing, the player's stance can be changed to standing, and its capsule height changed to the character's standing height. And finally, as always with a new mechanic, I'll update the character input in the player class. Now the player capsule should be resizing correctly when the player crouches and it uncrouches, but we still need to change the speed that the character moves based on its current stance. And it looks like I accidentally made the crouch height the same as the stand height, so I'll fix that and then we can test it out. Alright, it looks like the height of the character capsule is changing correctly when I press crouch, but the camera height is not changing at all. We could make the camera target a child of the character root and scale it up and down, but I'd rather define the camera's crouching and standing heights explicitly so it can be positioned independently from the root. These new stand and crouch camera height variables represent a normalized height that determines how far between the bottom and the top of the character capsule the camera target is positioned. Since they're both values between 0 and 1, I'll add a range attribute so they show up as sliders in the inspector. Then I'll make a new update function for updating the body of the character. Here's where I'll position the camera target and scale the root. We can calculate the camera target height by multiplying the current capsule's height by the current stance's camera target height variable, and then setting the camera target's local Y position to that calculated height. And since this is a new update function for the character, we need to call it from the player just like the others. Alright, hopping back over to Unity, the camera height now changes with the character's stance, and I can change the height of the camera when standing or crouching using these sliders. Next, I want to scale the character's root based on their stance so I can see in the scene view if the capsule is crouched. The player character doesn't have a reference to its root transform yet, so I'll add a new variable at the top, and then back in the update body function, we can scale that root up and down. Since the scale of the transform is not an absolute size, I need to figure out the normalized height and then use that for the root scale on the y-axis. I'm calculating the normalized height from 0 to 1 by dividing the current capsule's height by the character's standing height, and then using that as the y-axis of the root's target scale. And finally, I'll assign the root transform's local scale to this target scale we're calculating. Over in Unity, I'll hook up the character root in the inspector and then test it out. Now when the character crouches, everything is working correctly. The camera target is repositioned, the root is scaled down, and the movement speed is lowered. Now, I mentioned earlier that we need some extra logic to handle uncrouching, and that's because currently if you uncrouch under a low ceiling, the player stands up into the ceiling and typically ends up getting pushed through the floor. Let's go back to the uncrouch code and first check if the uncrouched character would be overlapping with the level before actually allowing it to uncrouch. I'll set the capsule height to the standing height like before, but won't actually change the character's stance to standing just yet. After standing up the capsule, we can then check if it's overlapping any colliders. The kinematic character motor provides a function for this called character overlap, which will pass the motor's position and rotation, as well as an array which will be populated with the overlapped colliders. I don't actually care what colliders the character overlaps with, just that it overlapped with any colliders at all. But the character overlap function needs it, so I'll go ahead and create that variable up top. Now, this function takes a lot of arguments, so I'm just going to try and reformat things a bit. Okay, that's better. Now, this function returns an integer, which tells us the number of detected overlaps. If any overlaps were detected, the player cannot safely stand up and should stay crouched. If the character didn't overlap with anything, its stance can safely be changed to standing. Now if I crouch, walk under this low ceiling, and then press uncrouch, nothing happens. If I walk out from under the ceiling and press uncrouch again, the character is able to stand up. With crouching, jumping, and walking implemented, all the basics are in place and we've got a solid foundation to build on. Before adding the slide mechanic, there are a few rough edges I'd like to polish. The crouch animation snapping up and down is a bit jarring, so let's start by animating that. I'll add a new field to the player character called Crouch Height Response, which controls how responsively the character's height animates. Because the character's height is now going to be animated over time, we need to know how much time has passed since the last frame. So now let's pass delta time to the update body function from the player. I'll create a new variable for it here and then pass it to the update body function. Rather than setting the camera's target position directly, it can be animated towards its target height over time using lerp damping. I think a lot of Unity developers are probably familiar with a function like this that smoothly animates some current value towards a target value over time. But even though it takes the delta time into account, this function isn't actually frame rate independent. The speed of the animation will be a little bit different at high frame rates versus low frame rates. I'll be totally honest, I don't totally understand why, but I'm happy to take the word of people smarter than me on this one. I found this article which explains the alternative that I've been using for a while. So wherever I normally write this t value, I write this instead. It's pretty similar to the original method, but is better at remaining frame rate independent. The camera's target position should now animate smoothly over time, so let's do the same thing for the scale of the capsule. Back in Unity, the crouch animation transitions smoothly over time rather than snapping up and down immediately. Next, I want to add the same smoothing to the character's movement. Right now, the acceleration is immediate, so if I press forward, the character is immediately walking forward at its target walk speed. So just like the crouch animation, let's add two new variables for the walk and crouch movement responsiveness. Based on the character's current stance, the appropriate response variable will be used to animate the character's velocity. By lerping the current velocity towards the new velocity, rather than assigning it directly, we can control how quickly the character accelerates when walking versus crouching. Now the movement feels way better. The smooth acceleration makes it feel much less rigid, and it's a lot easier to move around on platforms. The jumping is still not amazing, but there's a few things I can do to improve it a lot. Let's start with what I'm calling jump sustaining. It's a pretty common thing in platformers, where if you tap jump, the character does a little hop, whereas if you hold it, the character does a long jump. 2D games like Mario and Celeste have this mechanic, but it feels good in 3D as well, especially when precise jumping is important. Let's start with the input. Jumps will be sustained if the player is holding the jump button, so I'll add a new bool that the player will set to true as long as the jump input is held. This is different than the other jump bool, which is only true on the frame that the jump input is pressed. An easy way to sustain the character's jump is to lower the gravity while the jump button is pressed, so I'll create a new variable for the jump sustains gravity multiplier, and another for whether or not it's currently being requested, which I'll update from the update input function. Now, just before adding gravity to the character, I'll apply the gravity multiplier if a sustained jump is requested, and then hop over to the player and assign the jump sustain input. Back in Unity, if I quickly tap jump, I do a little hop, and if I hold it, I do a large jump. However, this doesn't quite feel right to me. While I want the player to be able to hold jump to extend it a bit, I just don't want it to feel like the player is activating low gravity. Rather than always having low gravity when the jump button is pressed, I'll only use the gravity multiplier when the player is moving upwards. Once they reach the apex of their jump, regular gravity will be applied, and the player will fall back down to the ground like normal. We can calculate the current vertical speed the same way we did when fixing double jumping earlier, by using the dot product of the current velocity against the character's up axis. Then before changing the effective gravity, I'll first check if the character is actually moving up. Now I think this feels a lot better. The character always falls back down at the same speed, but seems to will itself higher when holding the jump button. The next thing I'd like to do to make the jump feel way better is to give the character in-air control. Right now, as soon as I jump, I have no control over movement until I hit the ground again, which makes platforming pretty frustrating. Let's start by adding some variables for in-air control. The airspeed will be the maximum speed the player can accelerate to, and the air acceleration is how fast that speed will change. This is kind of like the response variable used for grounded movement, but I'm not using the same naming convention because in-air movement will behave very differently. So if the character is in the air and is trying to move, we'll calculate its planar movement, which is just the requested movement on the XZ plane. This is just like the grounded movement vector, but instead of snapping to the ground, which we can't do because we're in the air, it will just snap to a flat plane. In addition to projecting our requested movement onto the in-air movement plane, I'd also like to calculate the character's current velocity on the in-air movement plane as well. This way we'll know how fast the character is moving relative to how fast it wants to move. The reason all the movement logic is happening on a flat plane is because I don't want the in-air movement to affect or be affected by vertical velocity at all. Now we can calculate the movement force by multiplying our planar movement by the move acceleration variable. Rather than adding it directly to the current velocity, which would let the character accelerate indefinitely, I'll first use it to calculate a target velocity, so I can then clamp it to the in-air speed variable from earlier. Finally, I'll apply a steering force by adding the difference between the target and current planar velocity. Let's see if this works. Okay, this is in fact not working. The character is definitely accelerating past its in-air speed, so I made a mistake somewhere. Okay, the issue was that I'm projecting the requested movement vector instead of the current velocity vector when calculating the current planar velocity. With that fixed, now I can steer in the air, but I don't move faster than the airspeed. Let me crank up the acceleration a ton so it's more obvious. There's actually a few issues with the way this in-air movement works, but I'm going to move on for now and come back to it when it actually becomes a problem. I think now is finally a good time to implement sliding, so I'm first going to create a large mountain with a ramp so we have more varied terrain to test it on. So we've got a mountain, but I also want to really quickly add a teleport function so it's easier to move around the level when testing sliding. I'd like to set the character's position here in this teleport function, but the kinematic character motor has the final say on its own position, so I can't change it directly. The motor does have a function for changing its position, so I'll add a new function to the character which wraps it without exposing the kinematic character motor to the rest of the project. I want to teleport at whatever I'm looking at when the T key is pressed, so I'll add some editor-only code to the player that raycasts from the center of the camera and teleports to whatever point the raycast hits. Now I can look to the top of the mountain and press T to teleport up there, which should be helpful for testing stuff out. Finally, I'm ready to talk about sliding. Here's how I'd like it to work. If the player starts crouching while moving on the ground, I want them to start sliding. This will be a new stance that has its own movement logic distinct from walking and crouching. When sliding, as long as the player keeps pressing movement input, the character should steer its velocity along the ground, slowing over time due to friction, and speeding up and down based on the steepness of the terrain. When the character's slide speed is too slow, it will transition back to a crouch. To do all of this, there's a bit of housekeeping that needs to be done though. It would be nice to know what the character's stance and grounding status was from the last frame, as that will be important for telling us if the player should start sliding this frame. So let's store the character's stance and grounding status in a new character state struct. Then we can easily store a snapshot of the important character info from the last frame. Since I'm moving the stance variable into the character state struct, I need to find and replace everywhere I was referencing the stance variable and replace it with the one stored in the new state variable. I'll need to update this last state variable at some point, but I want to be careful about how I do it. This is a variable the player character should be able to check from within its update velocity function, but I also want it to be valid for external code that may need to check it in the future at other points during the frame. In hindsight, I may be overcomplicating this slightly, but at the moment, I'm doing this by creating a temp character state variable. If I set the last state directly to the current state before the character updates, the update velocity and update rotation functions would not be able to check that last state variable. So the temp state allows me to remember the character state before the character updates, and then assign it to the last state afterwards. After the character updates, I also want to make sure the current state's grounded bool is synced with the character motor. It feels a little redundant to do this since the character motor already knows the grounding status, but I'd rather manage all the stuff I want to track myself so it's all in one place and external code doesn't have to care about the kinematic character controller asset. Okay, now that we're keeping track of the last character state, we have enough information to implement sliding. I'll start by adding a few variables to tune how the slide behaves. The slide start speed is the minimum speed that the player will be given when the slide begins. This will give the feeling that the player is lunging into the slide. The slide end speed is the minimum speed the character can have while still considered sliding. If the slide speed is lower than this, the character will switch to a crouch. Finally, the slide friction is the rate at which the player will lose their slide speed. Let's also add a new stance for sliding. The character will only be able to be in this stance when on the ground, so to organize things a bit, I'll move the regular grounded movement code into its own scope. The first thing we should figure out is when the player should start sliding. I don't want the player to start sliding every time they crouch, so it should only happen when the character begins crouching while moving. I'll pop this grounded movement vector out of the movement scope since it can be shared between the standing, crouching, and sliding stances. The character will be considered moving if its grounded movement vector is non-zero. In addition to moving, the character also has to be crouching, but just because the player is moving and crouching doesn't mean they should start sliding. It should only happen if they started crouching this frame. I'd also like the character to start sliding if they hit the ground in a crouch, so if the player was standing or in the air last frame and are now crouched and moving, they should start sliding. When the player starts sliding, we need to figure out how fast they should be moving. The player might be moving faster than the slide start speed, so the slide start speed is really just a minimum speed the character is given when a slide begins, because if the player is moving faster than it, we don't want to slow him down. I'll then snap the current velocity to the ground surface, similarly to how we do when walking or crouching. The speed of the velocity will be the slide speed we calculated. Also, now that we have a slide stance, we need to update our movement code a bit, since the character should only move regularly when standing or crouching. So if the character is not standing or crouching, we know it's sliding. To start, I'll just apply friction, and change back to the crouch when sliding too slowly. Let's see how it works. It's a little hard to tell that I'm sliding normally because we don't actually accelerate downhill yet, but I set the slide start speed to 100 to compensate, and it appears to be working. Now I am noticing an issue where if the player gets air while sliding due to jumping or ramping off of a slope, they stay sliding in the air and get the slide start speed boost again when touching the ground. The player should only be able to slide on the ground, so if the character is sliding and finds itself in the air for any reason, I'll change its stance to a crouch. I also don't want the player to stay crouched or sliding after jumping, so I'll request that the character uncrouches when that happens. Now if I slide and jump, the character stands up. But if I jump and crouch in the air, I still start sliding when I hit the ground. The sliding is still pretty bad because you can't steer at all, you just go in a straight line until you slow down enough to start crouching. The sliding is also still unaffected by the steepness of the terrain you're on, so you don't go faster when sliding downhill, or go slower when sliding uphill. I'll start by adding steering to the sliding. This will behave similarly to the in-air movement, where the player is simply steering whatever velocity it has, rather than dictating it outright. For this, let's create a new slide acceleration variable, which will control how strong that steering force is. To steer the character, I want to first find the target velocity, which is the velocity the player would like to have based on their movement input. Then, again, similarly to in-air movement, we'll look at the difference between the current and target velocity to create a steering force. If we make the slide steer acceleration a large enough value, the steer force could potentially accelerate beyond the target velocity, which I definitely don't want. As the name suggests, steering should simply redirect the velocity, not make it go faster. Somehow we need to remove any part of the steer force that would cause the player's speed to increase. We could probably do this by projecting the steer force onto a plane, using the current velocity as its normal, but I'm just going to create a variable to store the current speed before the steer force is added. And then after adding the steer force to the current velocity, I can clamp it to its original speed. This allows the steer force to change the velocity's direction as much as it wants without increasing its speed. Alright, let's see if steering works. Okay, so I can still slide, and while sliding I have a bit of steering control. I'm going to increase the steer acceleration a ton just to make sure there isn't anything weird with how it works. So it looks like with a very high steer acceleration, I can change direction very quickly, but the speed of the slide is unaffected by that steering. Next, let's add slope-based acceleration to sliding, so the player accelerates downhill and deaccelerates uphill. The slope acceleration will be based on gravity. I want to tune this separately from the in-air gravity, so I'll make a new slide gravity variable. Then, hopping back to the slide code, I'll add a new scope for the slope acceleration. The acceleration will be a downwards force along the character's up axis, which is projected onto the ground surface. This way, if the ground is flat, the acceleration will be negated, but as the slope gets steeper, the acceleration approaches its full strength, or the slide gravity. Now if I slide, I can still slide like before, but if I slide up a hill, the slide slows down faster, whereas if I slide down a hill, it gains speed. Sliding seems to work fine here, but let's teleport to the top of the mountain and try sliding down a few times to make sure everything continues working as expected. So I'll just start walking and begin crouching to slide, and it seems to work pretty well. I was able to slide all the way down the hill, which is great, but let's teleport back up one more time to test how sliding works when combined with jumping. So I'll slide back down, and then jump. That may have seemed alright, but let's do it one more time and pay close attention to the player's velocity as soon as I jump. There it is. As soon as I jumped, I lost almost all of the speed from the slide, which does not feel great for a movement shooter. The reason we're losing all that speed in air is due to our in-air movement logic. If you recall, I mentioned there was issues with it that we'd fix when it became a problem. Well, it's becoming a problem now with sliding. Here's our culprit. The target velocity is clamped to the character's airspeed, which is currently 15 meters per second. So as soon as we jump in the air and try to move in any direction, the player's speed is quickly clamped to 15. The reason we're clamping it is so that the player doesn't accelerate indefinitely in the air due to direct movement input. However, if the player happens to be moving very quickly, like we just saw when sliding, we want to preserve that speed. So somehow, we need to accelerate the character such that when going faster than the max airspeed, any movement acceleration that would cause the player to move even faster is negated. And when moving slower than the max in-air speed, the character can steer itself like normal. I'll move our original code into an if statement that checks if the current speed is less than the in-air speed. Otherwise, we need to nerf any part of the movement force that would cause the player to accelerate faster. To limit the movement force, I'll project it onto a plane whose normal is the current velocity. This will negate any part of the movement force that's in the same direction as the current velocity, which prevents it from accelerating further. Now if I slide and jump, the character maintains its speed in the air. Another thing I want to address is air climbing. If I walk into a very steep slope that is so steep it isn't considered stable ground, the character can't walk up it, which is good. But if I jump into it, there's certain scenarios where I can almost ride the wall. It's definitely not an intentional mechanic, so I'd like to prevent it from happening. We've been using the character motor's is stable on ground flag when checking the player's grounding status, but when in the air, we need to check the found any ground flag, which will also be true for very steep ground. As our code currently stands, we don't handle touching the ground at all in the air because, well, the character's in the air. But as we've seen, being in the air versus on the ground are not mutually exclusive states. The player can still technically be touching the ground in the air, which we need to handle now. I'll start by checking if the movement force is contributing positively to the overall movement direction, by taking the dot product of the movement force against the new velocity. If the dot product is greater than 0, it tells us that the character is roughly trying to move in the direction they're already moving. If the dot product was 0 or negative, it would imply that the player is trying to steer in a new direction, which should be fine. So if the character is continuously accelerating into some ground while they're in the air, we need to prevent air climbing. To prevent air climbing, we need to remove any movement force that would push the player further into the slope. Since air movement is done on the XZ plane, I'll calculate an obstruction normal on the XZ plane using two cross products. This vector is like a flattened version of the ground normal. By projecting the movement force onto a plane with that obstruction normal, any velocity that would push the player into the slope is removed. This allows the player to move side to side and backwards, but prevents them from continuously accelerating into steep terrain. Now if I jump into a wall, the character falls back down like normal. Another thing I want to test is how well momentum is preserved when hitting the ground in a slide. Ideally, I should slide faster if I fall into it first. Before testing it, I'm going to set the slide's start speed to 0. This way it will be easier to see how much speed is carried over from the fall into the slide. So here I'm jumping into the air and crouching, but most of the time I hit the ground, the slide doesn't appear to have any speed. So something is definitely wrong here. If we scroll up and look at the code for starting a slide, it actually seems fine. The slide start speed should be faster if the current velocity is large enough. So the current velocity must be being changed somewhere unexpectedly. To help figure out what's going on, I want to debug the character's velocity so we can see what it looks like before and after the character hits the ground. I'll add a new velocity field to the character state struct so we can track it, and then update it along with the grounded flag after the character updates. With the velocity being tracked from the last frame, we can go to where the character starts sliding in code and draw two debug lines, one for the character's velocity this frame, and another for the character's velocity on the last frame. If they don't look the same in the game, then we'll know something's wrong. I'll try falling into a slide again, and then pause the editor. This time we'll be able to see the velocity after the player hit the ground drawn in red, and the velocity before the player hit the ground in green. Clearly the player is losing a lot of velocity when it hits the ground, but we aren't changing it, so it must be the character motor. I poked around and tracked it down to the kinematic character motor's handle velocity projection method. Under certain conditions, the character velocity is projected onto a flat plane when they hit the ground. This prevents the player from sliding when they hit the ground. For normal movement, this is good, but in our case, sliding is an intentional mechanic, so we don't always want it to happen. I don't think we can easily change this logic without making our own character motor, but since we're tracking the velocity ourselves, we can just reproject it from the last frame when the slide starts. Now, when I run and crouch in the air, the character keeps its speed when hitting the ground in a slide. Great. Okay, sliding is almost done, but there's one last issue. It's a bit tricky to explain, so to help visualize the problem, I'm first going to create a quick shader for the terrain that draws a red color wherever the ground is too steep to walk on. This will be helpful for showing when the player is on stable ground versus unstable ground, because yet again, that's where the problem crops up when sliding. Now you can see the parts of the terrain that are too steep to be considered stable. So whenever the player is standing on these parts, they aren't actually standing and will fall. So if the player is crouching or sliding and moves onto the unstable red part of the terrain, they fall back immediately to the white stable part of the terrain. For a brief moment, the character is considered falling, and when the player lands back on stable terrain, they're in a crouch. We've programmed the slide to start if the player hits the ground in a crouch, so the player starts sliding with a speed boost seemingly out of nowhere. This doesn't quite feel right because the player never intentionally air crouched. It just happened automatically when the player left the ground for a moment, walking onto unstable terrain. Because of this, the player can enter a feedback loop of sorts, where the player starts sliding over and over again, riding the edge of stable and unstable terrain, getting a slide speed boost whenever they touch the stable ground again. At the risk of over-explaining this, I want to draw a debug ray for the player's velocity to see when and where each slide occurs. Now let's test it one more time. After crouching and walking into the unstable part of the terrain, the player will become ungrounded and fall back down in a crouch, at which point the player will become grounded again and begin sliding with a slide start speed. These green debug lines are showing the character's velocity every time it starts sliding. And keep in mind, I never intentionally started sliding, I simply walked onto unstable ground in a crouch and fell back down. The difference between this scenario and the one where we jump into the air and crouch is that air crouching requires the player to intentionally press the crouch button. This slide on the edge of unstable ground is not intentional, which I'd like to fix. We can isolate the unintentional sliding by remembering if the player pressed crouch in the air. If the player hits the ground in a crouch, but didn't press crouch in the air, we'll know the slide shouldn't start because sliding should only happen due to direct player input. So if the player just started requesting a crouch this frame, we'll set the new requested crouch in air flag to whether or not the character is in the air. Otherwise, if they just requested the character should uncrouch, we'll set it to false. This flag should also be set to false whenever the player jumps in the air. Then when the character starts sliding, I'll calculate an effective slide start speed. This speed will be 0 if the player hit the ground in a crouch and didn't request that crouch in the air. I'll also reset the air crouch flag now that the character has hit the ground. So let's see if this works. If I crouch and walk into the unstable ground, the character slides back down without being given a speed boost. So now the sliding is working a bit better and we can move on. One thing I've left unaddressed for a bit is the fact that the player can jump as many times as they like in the air. I may add double jumping again later, but for now I'd only like the player to be able to jump when they're on the ground. So before jumping, let's first check if the character is grounded. When grounded, the character can jump like before, but if not, the jump request will be denied by setting the requested jump bool back to false. Now I can press jump as many times as I like, but the character only jumps when on the ground. One additional thing I'd like to do is add some leniency to the grounding check. It's pretty frustrating to do a running jump off of a ledge, but press the jump button a frame or two too late and not jump at all. The same is true when falling and pressing jump just before the player hits the ground. I want to always respect the player's intention whenever possible, and to do that for jumping, I want to add coyote time. This is an informal term that describes the brief period of time after leaving the ground in which a character can still jump. I'll define a new coyote time variable that determines how long the grace period is when jumping in the air. This will give the player 0.2 of a second where their jump input can be buffered before hitting the ground while also being accepted after leaving the ground. Both of these timings need to be tracked, so I'll create 2 new fields for them as well. These timers need to be ticked and reset appropriately, so I'll start with the jump request timer. This timer should be reset whenever a jump is first requested, so I'll go to the update input function and set the timer back to 0 if a jump was requested this frame. Then for the ungrounded timer, I'll set it back to 0 every frame that the player is on the ground, and increment the timer when the player is still in the air. Let's now check if the player can jump or not due to coyote time. If the character can't jump now, but a jump is requested, we'll tick the time since jump timer. Rather than denying the jump request outright, I'll set it to false only if the coyote time is passed. Now the character should be able to buffer a jump early or execute a jump late, as long as it's within the coyote time grace period. I'll lower the timescale so we can look at the player jump in slow motion. As you can see, I'm able to jump for a split second after leaving the ground, but can also buffer a jump input a split second before hitting the ground. As is often the case, there's a subtle issue with the initial implementation. If the player is on the ground and jumps, the player can then immediately jump again in the air as long as it's within the Coyote time grace period. So the player can jump twice in a row if they press the jump button twice in quick succession. What we need to do is keep track of whether or not the character was ungrounded because they jumped. And if so, we won't allow a Coyote jump. I'll create a new field to record if the player was ungrounded due to a jump. This flag should be reset to false whenever the player is on the ground. But whenever the player jumps, we'll set it to true. And I'll only allow Coyote jumping if the character wasn't originally grounded due to a jump. Now if I press jump twice in quick succession, the character only jumps once, but if I remove that condition, the player can jump twice again. With that fixed for Coyote jumping, I'm ready to move on to the player camera. Camera motion is how we'll really ground the character's movement and help the player feel what the character controller is doing. Right now when the character jumps up and down, it feels very stiff. The camera has no continuity and feels lifeless. When something isn't feeling good like this, I typically turn to animation principles to figure out why. While it isn't always practical to use them since video games have to be responsive to user input, unlike traditional animation, it can still serve as a north star for what I'd like the gameplay to look like. In this case, from an animation perspective, you could say the camera movement is missing follow-through and overlapping action. When the player jumps, I'd like the camera to lag behind somewhat, and when the player lands, I'd like it to overshoot its desired position before settling. Rather than making bespoke animations for these scenarios, I'm going to instead simulate the camera as if it's attached to the player by a spring. This would result in procedural camera movement that feels connected to the character's movement. Inside a new camera spring script, I'll create an initialization and update function like our other scripts. Then I'll hook it up to the player. The camera spring will be a new game object that's a child of the player camera. In the future, we can add more objects to the player camera hierarchy to additively animate the camera in other ways. The spring physics will be set up to affect the camera's rotation in addition to its position. Changing the camera rotation needs to be done very carefully to avoid motion sickness in players, and in an actual game, I'd add settings to allow players to disable it entirely. I'll start by simulating a spring following the camera's position. So let's create a new field for the spring position and velocity, and then initialize them both. For the spring math, I want to use the numeric springing function from this article. I've translated the function into C# so it can be used in Unity. The function takes in a current position and a target position, as well as a current velocity. It's meant to be called every tick, and given a time step, it uses spring physics to affect the current position and velocity. The half-life and frequency arguments change the characteristics of the spring in motion. Frequency determines how quickly the spring resonates, and the half-life determines how long it takes for the strength of the oscillation to be reduced by 50%. So with a half-life of 2, the oscillation would be dampened by 50% every 2 seconds. Now let's add parameters for the spring function here. The spring should remain very subtle and decay very quickly, so the half-life is going to be extremely short. The frequency should be high enough that the spring doesn't lag far behind the player, but low enough that it doesn't feel like it's vibrating. I'll also create 2 additional fields to control how much the spring offsets the camera's rotation versus its position. Now let's simulate the spring and visualize it so we can see what's happening. To visualize it, I'll draw a line and sphere gizmo pointing at the spring's position. You can see the spring in green following the player. It lags behind the camera's rest position when jumping, and then overshoots when landing. The spring isn't affecting the camera yet, but we can use its position to drive the procedural camera animation. By calculating the spring's position relative to the camera's target position, which is just the transform, we can figure out how far it is above or below the camera. The height difference can then be used to offset the pitch of the camera so it tilts up and down based on the spring's position. To figure out how far above or below the camera target the spring position is, the camera spring needs to know which direction up is. So I'll pass the up vector to the update spring function from the player, which has access to the camera target's up vector. Then, using the dot product of the local spring position against the up direction, we can figure out how far above or below the camera target the spring is. The spring height can then be used to offset the transform's local pitch. I think this feels a lot better. It adds more life to the camera movement without affecting the responsiveness of look input. While this isn't necessarily physically accurate, I think that's okay with me. My goal is just to ground the character and help the player feel the physics have continuity, even at a subconscious level. In addition to offsetting the rotation, I'd also like to offset the position a small amount using the linear displacement field. Since the spring math uses the transform's position as a target position, I'll reset the transform's local position at the beginning of its update to prevent a feedback loop. Then at the end of the update, we can set the transform's local position to the spring's local position multiplied by the linear displacement amount. The linear displacement is very subtle because I don't want the camera to be offset outside of the player's capsule. All in all though, I think it's actually starting to feel really good to play. The character controller's movement is working well, and the camera spring adds an additional layer of polish that brings it all together. The next thing I'd like to do is add camera leaning. I want the player's camera to lean into their acceleration so that the head leads the character's movement. This is another effect that really needs to remain subtle and should have a setting for disabling it in-game. I'll first create a camera lean component and hook it up to the player. Like the camera spring component, this will need to be passed a float for the delta time and a vector so it knows which direction is up. It will also need to know the player's acceleration. All of this will need to be passed to the camera lean component from the player, so let's hook it up there. Now, the player doesn't actually know the character's acceleration right now, so I'll leave it blank for a moment. To get the acceleration, we'll need to expose it from the player character. It can be added as another vector to the character's state struct. The first thing I want to do is reset the acceleration at the beginning of the velocity update. Then, when the player moves, before writing directly to the current velocity, I'll store it in a variable. This allows us to calculate the acceleration by looking at the difference between the current velocity and the new velocity stored in the move velocity variable. After updating the acceleration, we can update the current velocity to the new move velocity. I'll do the same thing with steer acceleration when sliding. So we're really just calculating the acceleration that contributes to direct movement input. It's not the raw acceleration because any forces like gravity are excluded. If I ever have the need for raw acceleration, I'll rename this field to make the distinction more clear, but for now I think this is fine. Lastly, I'll add two new functions that expose the character's state to the player. One is the current state, and the other is the character's last state. Then, back in the player, I'll fetch the current character state and pass its acceleration to the camera lean component's update lean function. For now, I'll just draw a debug line to visualize the acceleration vector, and verify it's being calculated correctly when viewed in slow motion. It appears to be updating correctly based on my movement input, but it's still quite erratic. If we're going to use this vector to animate the camera, it will need to be smoothed out quite a bit. To do that, I'll create a new vector for the damped acceleration, which will be a smooth version of the acceleration that's passed to the function. Then I'll create two new floats for controlling the damping. The attack damping will be used when the input acceleration is greater than the damped acceleration. And we'll use the decay damping when the target acceleration is less than the damped acceleration. Instead of using lerp damping like we've done for other parts of the character, I'm going to use the smooth damp function since I don't want the camera lean to have an infinite decay. The smooth damp function requires a velocity similarly to the spring function from earlier. The naming for this variable is a bit weird because acceleration has a velocity, which sounds backwards, but in this case the damped acceleration is being smoothly animated towards the input acceleration, so it needs a velocity. Now to decide between the attack and decay damping, we need to compare our input acceleration to the damped acceleration. I don't want to use the input acceleration directly because I only want the camera lean to be affected by planar acceleration. In other words, the player should only lean when moving forward and back or side to side, but any acceleration up and down should be ignored. So rather than using the input acceleration directly, I'll project it onto a flat plane. Then we can use the smooth damp function to animate the damped acceleration towards the planar acceleration over time. Now let's draw the damped acceleration to visualize it. You can see the damped acceleration drawn by the blue line and how it smoothly follows the input acceleration in red. It does look a bit slow, but that's just because I have the time scale lowered right now. Now I want to figure out an axis of rotation for the camera to lean around based on that acceleration. We can do this pretty easily by taking the cross product of the acceleration vector against the character's up axis. Before rotating this object, I'm going to first reset its local rotation so it's the same as its parent. Then we can rotate the transform around its lean axis based on the magnitude of the acceleration. The more the character is accelerating, the more the camera will lean. Also, I caught a mistake in the acceleration calculations of the player character from earlier. The acceleration should be divided by delta time, since acceleration is a change in velocity over a change in time. Okay, so it works, but it's a bit much. This might be good for a drunk simulator, but definitely not a movement shooter. To lessen the effect, I'll add a new strength variable and then multiply the rotation angle by it. This is definitely feeling better. It could use a little bit more work, but it's subtle and it makes the camera feel more dynamic and communicates acceleration to the player. As an extra small touch, I'd like to have a larger lean strength when sliding. I'm looking for any opportunities to differentiate sliding from crouching so that it's super clear to the player even without a UI indicator. We'll need an additional strength variable for the slide strength, but we'll also need to pass another argument to the update lean function so it knows whether or not the character is sliding. Over in the player, we can just check if the stance is sliding and then pass true if so. Then back in the camera lean component, we can calculate an effective strength based on the sliding bool. Now, I don't actually want to use this effective strength directly because it can snap between the slide strength and walk strength in a single frame. Let's smooth out the lean strength in a similar way to how we're smoothing out the acceleration vector. The effective strength will simply be a target value that a smooth strength variable animates towards over time. So let's create that variable. I'll also create a new variable for the strength response and initialize the smooth strength to that walk strength. Then we can lerp damp the smooth strength towards the effective strength, giving us a lean strength that changes smoothly over time. Now when sliding, the camera leans a bit more and feels different. I'd say this is decent, but I'll probably revisit it again at some point. The next thing I'd like to add is a vignette effect. When the player is crouched or sliding, I want to add a subtle darkening around the edges of the screen as another way to help the player intuit the state of the character. So I'll enable post-processing on the player's camera, and then create a new empty child game object called effects. On that object, I'll add a volume component which handles the post-processing. I won't assign a profile to it because this volume will only be changed at runtime. Any other post-processing effects can live on a different volume separate from the player. This will be controlled via a new stance vignette script, which will manage animating the vignette when the player's stance changes. The stance vignette will be initialized with the volume profile. This is what holds the post-processing settings for a volume. To update the vignette, we'll also need to know the current stance and the delta time. Then we can go over to the player and hook it up like usual. The stance vignette can be initialized with the volume's profile. This profile property's getter automatically generates a new volume profile instance, so we don't have to create one ourselves. Then we can update the stance vignette alongside the other camera components. Now let's set it up in the scene and hook it all up to the player. In the stance vignette, the first thing we need to do is get the vignette effect from the volume profile and create it if it doesn't exist. I don't know why VS Code is whining about these function calls, but it's wrong and the code is fine, so ignore the error squiggles. The vignette has an intensity property, which controls how much the screen edges are darkened, so I'd like to animate it between a min and max value based on the character's stance. Let's define those variables now. I think the player camera should have a little bit of vignette even when standing, so I'll set the min value to a small number. The vignette intensity should also be more prominent when the player is crouching or sliding, so the max will be significantly higher. I'd also like the vignette to change smoothly over time, so I'll add a response variable like usual. When the script is initialized, we'll override the vignette intensity with our minimum value, and when the script is updated, we'll lerp damp the vignette's current intensity towards a target intensity based on our character's stance. Now we have a subtle vignette around the edges of the screen, and when the player crouches or slides, it darkens the edges further. As a last touch, I want to add a little bit of extra post-processing to the scene. There's a few specific effects I'll be adding. I like Panini projection because it allows for a higher field of view with a little bit less peripheral distortion from perspective projection. I'll also add a depth of field effect that's configured to render up-close surfaces out of focus. And finally, I'll add a bloom effect, though there isn't anything emissive in the scene, so there's not much for it to do at the moment. With that, we built a pretty solid foundation for a first-person movement game. I'll continue developing on it for my own game, and port over the other mechanics I'd previously implemented, like wall running and crouch slamming. There's also a lot of gameplay juicing I left out, since I could genuinely spend forever on that stuff. If you're looking for some other ideas on how to juice up your first-person character, here's a few ideas. To increase the feeling of speed, you can increase the camera's field of view as the player goes faster. Same thing goes for post-processing effects like chromatic aberration, which can look cool as an effect that fades in and jitters when the player is moving really fast. You can also juice up the camera motion a bit by adding different flavors of camera shakes. You could fade in one type of camera shake when sliding, so it feels like the player's moving over bumpy ground, or fade in a different type when moving fast in the air, so it feels like the wind is buffeting the player. I hope this has been helpful or interesting in some way. I have no idea if this video format is any good, so if you made it this far, definitely let me know what you think is or isn't working. I'd love to make more videos like this that aren't directly related to my game, so if you have any feedback or requests, let me know. That's all for now. Thanks for watching.